Welcome everyone. Thank you for being here. In this video, I will talk about my work on inverses and tame algebra estimates for product kernels and flag kernels on graded Lie groups. Before I begin, I would like to thank the organizers of the Happy series for giving me the opportunity to present my work. I would also like to say a few words about my future plans. So my name is Amelia Stokolosa. I am a graduate student at the University of Wisconsin-Madison, working with my advisor, Brian Street, and I will be graduating this year in May 2025. So I am currently looking for postdoc positions with a start date in fall 2025. Okay, so to talk more about the math here. So the setting is the following. Our question integrates ideas from three different subjects. The first one is the multi-parameter theory on product spaces. The second one is the study of inverses of singular integral operators, which is very useful when studying certain PDEs. And finally, when you're looking at the study of certain nonlinear PDEs, tame algebra estimates also pop up. So our question is going to integrate these three subjects. To talk about the non-commutative setting, the setting is the following. So we are going to be looking at graded Lie groups, the simplest of which is the Heisenberg group. The Heisenberg group is special. It can be identified with R3, where 3 is its topological dimension. The only thing you have to keep in mind is there's a non-commutative group operation. So this non-commutative group operation is going to be a big obstacle in our problem. So from now on, whenever you see the notation G, this stands for a graded Lie group, which can be identified with RQ for some integer Q. To define the multi-parameter setting, first, we need to define single parameter dilations. This is best explained with an example. So again, focusing on the Heisenberg group, you can pick a positive number R and define the dilation R onto any element of the Heisenberg group as follows. You multiply the first two coordinates in the element by R, and because of the twisting that gives the non-commutative group operation a non-commutative flavor, you have to square the last. You have to square the positive number you pick in the last coordinate. So with these single parameter dilations, you can define multi-parameter dilations. To focus on the key ideas and not get too caught up with the details, we're going to focus today in this video in the two-parameter setting, the biparameter setting. So we're looking at two graded Lie groups, and we're taking the direct product of two graded Lie groups. On each graded Lie group, you have single parameter dilations, which, for example, as you can see up with the Heisenberg group case, are non-isotropic. And with these single parameter dilations, you can define biparameter dilations on the direct product of the two graded Lie groups. So the objects we're interested in are multi-parameter singular integrals. So we're going to consider in particular left invariant singular integral operators. So left invariant operators are given by right convolution with a kernel K. The kernel K is going to have some interesting properties. It is going to be almost homogeneous with respect to multi-parameter dilations. Multi-parameter dilations as they were defined in our previous slide. To say a little bit more about these kernels that characterize our operators, they are given a name. So the kernels we're interested in are product kernels and flag kernels. Both of these are extensions to the multi-parameter setting of the single parameter Calderon-Zingman theory. So just like with the Calderon-Zingman theory, you need to define a growth condition, sometimes called the size condition, which says here that, let's look at product kernels for a second. The product kernels are identifiable with a smooth function away from the singularity. And away from the singularity, it can be identified with a smooth function with some nice decay properties. Similarly, flat kernels also satisfy a growth condition, which says that away from its singularity, the distribution can be identified with a smooth function with some nice decay properties. Now, the singularity for product kernels is across, so you have to stay away from T1 is equal to 0 and T2 is equal to 0. With flat kernels, there's more singularity in the first variable T1. So the flat kernels are smooth away from the coordinate axis T1 is equal to 0. So this defines our product kernels and flat kernels. This almost defines our product kernels and flat kernels, just like with the Hilbert transform, for example, or with Calderon-Zeeman kernels. To define these singular distributions, you also have to make sense of them with a cancellation condition. Now, this cancellation condition is defined recursively, and so to focus in on the ideas again, I will skip the details of this recursive definition. So this is usually where I stop and ask the audience if this is clear and if there are any questions before I move on. If there are any questions throughout this talk, feel free to email me. I'd be happy to respond by email. Okay, so with this setting, let's do a quick summary before we talk about our problem. We're looking at the direct product of two graded Lie groups. In particular, the objects we're interested in are left invariant operators given by right convolution with a product kernel or a flat kernel. The group convolution here is non-commutative, and so this is going to force us to go through a couple of new tools and strategies. And K here is the product kernel or a flat kernel. So our question is the following. If the operator is invertible in L2, is the inverse operator also given by right convolution with a product kernel or flat kernel? Now we can pause here and make a couple of observations. The original operator presents some nice singularity away from where T1 is equal to 0 and T2 is equal to 0 for the product kernel. So away from this cross. And we're not making a very restrictive assumption here, a very restrictive hypothesis. We're simply saying that the operator is invertible in L2, so the inverse exists and it's L2 bounded. And the question is asking whether the inverse operator is just as good as the original operator. Is the inverse operator presenting as much regularity as the original operator? Can I take as many derivatives as I want away from a certain singularity? Before I present the theorem, I should mention some past works. So there's been quite a lot of work on single parameter inversion theorems, starting off with the foundational work by Calderon and Zeeman in 1956, where they studied kernels on the Euclidean space. Later on, Chris Geller, Glowacki, and Polin studied the non-commutative setting. And I spent a lot of time looking at these two papers and building upon them. There's also been more recent work by Glowacki in 2017, where Glowacki studied kernels that were no longer homogeneous, that were almost homogeneous on a homogeneous Lie group. Now, these inversion theorems are motivated in differential equations. For example, in 1988, Chris showed that regularity properties of the inverse operator implies regularity properties of solutions of the boundary d-bar operator. So our multi-parameter inversion theorem extends the previous single parameter inversion theorems to kernels that are almost homogeneous with respect to multi-parameter dilations, as we defined in our first few slides, namely product kernels and flat kernels. And here's the statement of the theorem. Let op k be a singular integral operator given by right convolution with a product kernel. If we assume the operator is invertible in L2, then the inverse is also given by right convolution with a product kernel L. So the inverse presents as much regularity as the original operator. And with some modifications to the proof, you also obtain this result for flat kernels. So this is the theorem we're going to be proving. Before I move on, I should also mention some past work on multi-parameter singular integrals. Multi-parameter singular integrals were first studied by Pfefferman and Stein and Journet in 1982, 1985, in the Euclidean setting where they took Rn and decomposed it in certain ways. Rita, Ricci, and Stein studied flat kernels on Heisenberg-type groups, so a non-commutative setting. Naylor, Ricci, and Stein in 2001 studied flat kernels and product kernels in the Euclidean setting and on the direct product of homogeneous groups. And independently, Nagel, Ricci, Stein, and Wenger in 2012, 2018, and Glowacki in 2010 and 2013 studied flat kernels on homogeneous Lie groups. And finally, my advisor in 2014, Brian Street, developed a general theory for multi-parameter singular integrals. And I used a lot of the tools that were first presented in that work. So there are two proofs using tools from two different subfields for this theorem. The original proof from 2023 used tools from PDEs, so a bootstrapping argument, the construction of an a priori estimate to obtain the regularity properties for our inverse operator, commutator estimates, and using fractional Sobolev spaces as defined by fallen out stratified Lie groups and then easily extendable to the graded Lie group setting. The new proof uses tools from operator algebra. So it uses spectral theory, an Ullmann series, Tame algebra estimates, and the key idea here is the construction of a Fréchet topology. It's the construction of a family of semi-norms that are fine-tuned to encapsulate all the key features of the kernels of interest. Hopefully this is clear. To talk about the first proof using PDEs, the key idea to keep in mind is that the Fourier transform is no longer such a handy tool in this non-commutative setting. So we no longer have access to all the multiplier theory that is so useful in the Euclidean setting. So instead, to study our inverse operator, we're going to look elsewhere for tools, and we can use techniques from PDEs. The key idea here is that most operations here do not commute. The group multiplication does not commute. The group convolution is non-commutative, but right invariant differential operators commute with our left invariant operator op k. So we're going to make use of this commutativity by defining Sobolev spaces, right invariant Sobolev spaces, right invariant non-isotropic multi-parameter Sobolev spaces using this key identity. So our L mu's here are the right invariant sub-Laplacians on each graded Lie group. So with this key idea, we're going to define Sobolev spaces with which we can construct an a priori estimate. And the a priori estimate for product kernels, let's just focus on product kernels for a second, goes as follows. There's some notation here to parse through. The main takeaway here is the following. By introducing test functions, by introducing test functions, you get some smoothing. You can trade localization for smoothing. And here's how. You can plug in a distribution that's as rough as possible. And by introducing all these test functions, you obtain as much smoothing as you want. So S1 and S2 are positive numbers, and N1 and N2 are also positive numbers. So you can plug in something really, really rough and get an output that is as regular as you want. And this is the key a priori estimate that allows you to circumvent the problem of the Fourier transform and obtain the regularity properties of your inverse operator. And just to reiterate, we use multi-parameter, non-isotropic, right invariant Sobolev spaces, which are well adapted to our left invariant operator. Now moving on to the new proof. The new proof uses operator algebra techniques. It uses, this time, the key constructions are Tame algebra estimates. And let's say a little bit more about Tame estimates. So Tame estimates, maybe some of you have heard of them before. They're central to the study of nonlinear PDEs via the Nash-Moser inverse function theorem as formulated by Hamilton, by Hermanda. So Tame estimates are central to the study of nonlinear PDEs. Tame-like estimates also appear under the name of Caton-Ponce inequalities and fractional Leibniz rules. And these are extensions of the following product lemma. So what does this product lemma tell you? The HS norm of the product of two functions can be bounded above by the two extremal terms. So when you apply the Leibniz rule to the product of two functions, let's say you take a very high degree derivative. There are some intermediate terms where the derivatives are going to hit both f and g. But this estimate here is telling you that the intermediate terms are bounded above by the extreme terms where all the derivatives either hit f or all the derivatives hit g. And you take the L infinity norm without taking any derivatives of the other function. So this is a stronger estimate than the estimate that would follow from the Leibniz rule. Now, our estimate, it's a good idea to keep this elementary estimate in mind before looking at our multi-parameter estimate, which goes as follows. If you take two product kernels, K and L, and you define some semi-norms of where the regularity is measured by K1 and K2, this semi-norm is bounded above by a sum of a zero norm times a K1, K2 norm plus a K1, K2 norm plus a zero norm. So again, the intermediate terms where the derivatives hit both K and L are bounded above by the extremal terms where all the derivatives either hit L or K, and no derivatives hit K or L. Now, I should maybe say a few words about this notation here. This is the notation for the L2 operator norm. In the multi-parameter setting, this would not be the best you can hope for. So I'm sweeping a lot of stuff under the rug. What I'm sweeping under the rug are some extra terms that pop up in the multi-parameter setting. In the multi-parameter setting, the best you can hope for is this estimate, which you can prove by constructing semi-norms in a careful way. And again, the key idea is all the derivatives, let's focus on the derivatives on the first factor, G1. So the derivatives are, you're taking up to K1 derivatives, and they either hit K or L, but not both. So note here that all the derivatives are going to hit L here. All the derivatives on the first factor are going to hit K in the second term, but not L. All the derivatives in the first factor are going to hit L in the third term, but not K. And finally, in the fourth term, all the derivatives in the first factor are only going to hit K and not L. So this is a Tame algebra estimate for product kernels. Why is it called a Tame algebra estimate? This estimate is tame because the highest order seminorm in each parameter, 1 and 2, appears only once in each summand. So K1 is only going to appear once in each summand. Similarly, if you flip and you only look at the K2 regularity. These estimates are called Tame algebra estimates because we compose K and L together via the non-commutative group convolution. So the group convolution here stands for taking the product of two functions in our earlier slide. To obtain this Tame algebra estimate, I hinted at this earlier on. The main idea is the proof is the construction of a countable family of seminorms, which I'm denoting as follows here, which are adapted to product kernels. And I also obtain a countable family of seminorms adapted to flat kernels. But let's focus on product kernels here. So the key construction of these seminorms that give rise to a Fréchet topology needs to satisfy two conflicting characteristics. On the one hand, you want the seminorms to be amenable to an L2 theory. This allows you to, in the last step of the proof, use the spectral theorem to obtain an inversion result. So you want the seminorms to be amenable to an L2 theory. But on the other hand, you want to encapsulate the behavior away from each branch of the cross by introducing test functions in a meaningful way. And there's a little bit of work and fine-tuning that needs to be done here to obtain the right seminorms. To obtain the right seminorms, I build upon two previous constructions. The first is a single parameter construction by Chris Glowacki and Polin from 1992, and I hinted this paper earlier on, where they construct seminorms for homogeneous distribution in the single parameter setting. What do they do? Well, homogeneous distributions can be written in this way as a decomposition, where they take the absolute value of the scale of the Dirac function and measure the regularity where the input is comparable to 1 of the remaining part of the kernel. Take the L2 Sobolev spaces. The other construction I build upon is a multi-parameter construction by my advisor, where the idea is as follows, and I only included the single parameter seminorms here to keep things a little bit simpler. Here there's a seminorm defined, which instead of using Sobolev spaces, uses a duality type construction. And using these two constructions, you can obtain a class of seminorms for product kernels, which gives rise to a Tame algebra estimate. And I would like to conclude this video by thanking again the organizers of the Happy channel for giving me the opportunity to give this talk. I would like to thank my advisor, Brian Street, and the NSF for supporting my research. Thanks again.